Alrighty. When I get to example 5, and example 5 and 6 are the last problems in this section, again, we're just in video 3, we're continuing to do more practice with L'Hopital's rule. The subsequent video after this one, again, is an optional video. If you want to know where did L'Hopital's rule come from, we can talk about that. But for this, well, we have to check. Does it even qualify? If I take the limit as x approaches 0 of g prime of x minus 6 cosine 4 times x, do I get 0 or infinity? And if I take the limit as x approaches 0 of f of g of x, do I get 0 or infinity? Let's see. G prime of 0. So I go back. G prime when x equals 0 is 6. So then this is 6 minus 6 times the cosine of 4 times 0. Well, 4 times 0 is 0. Cosine of 0 is 1. So then I get this, and that indeed gives me a 0 in the numerator. Okay. What about the denominator? Well, I have to substitute 0 in for g, and when I plug it in for g, g of 0 is 0. So then this is going to be f of 0, and f of 0 is 0. So yes, this does qualify for me to use L'Hopital's rule. And as I start to write L'Hopital's rule setup here, I realize I already have the first derivative. But L'Hopital's rule says to take the derivative of the numerator. So that means we're going to have to find the second derivative, because it's the derivative of the derivative, minus 6 times the derivative of cosine. Actually, the derivative of cosine of 4x. So this is an inside-outside situation. So the derivative of cosine is negative sine. So it's going to turn it into this. With the inside still in it, times the derivative of the inside, which is 4. All over f of g of 0. I'm sorry, that's not true. I got to find the derivative. The derivative of the outside, with the inside still in it, times the derivative of the inside. I fell asleep there and I didn't catch that. This is what I have to evaluate. Alrighty, well, according to the numerator, I need to find g double prime of 0. G double prime of 0 would be g double prime at x equals 0 is 2. So this first part in the numerator is 2 plus 6 times the sine of 4 times 0. Well, 4 times 0 is 0, and sine of 0 is also 0, times the 4. This whole thing is going to vanish. That's just 0. Divided by f prime at g of 0. Okay, so I'm looking for g of 0. G at 0 is 0 times the derivative of g at 0. The derivative of g at 0 is 6. So times 6. But I still need to find f prime of 0. So I go back to my table. What is the slope of the line at 0 when x equals 0? Well, it's still negative 1 over 2. So then this is negative 1/2. Which then leads me to 2 in the numerator, negative 3 in the denominator, and there's my answer. The whole idea is there's a shortcut way to find limits, but only if we have indeterminate forms. Then I can take the derivative of the top, the derivative of the bottom, and try the limit again. Don't do the quotient rule. That's not what it's saying. It says to find a limit, you can use this shortcut rule in order to figure that out. And then finally, example 6. Again, need to verify. If it doesn't produce an indeterminate form, then it doesn't work. I can't use L'Hopital's rule. If you look at the denominator, negative 2 squared is 4, plus 4 times negative 2 is negative 8, plus 4, I believe that's 0. And now using my table, g of negative 2, g of negative 2 is negative 4, plus negative 2 squared, that's negative 2 times negative 2, that's positive 4, and that is 0 as well. We're in business. We can do L'Hopital's rule. So let's try it. The limit as x approaches negative 2. So if you want, you can pause the video here and see if you can start this out, and then we'll check it once you unpause. So I'll give you a couple of seconds to pause the video and see if you can do the derivative of the top over the derivative of the bottom, and then reevaluate the limit using those new expressions. Here's what it would look like. Take the derivative of the top over the derivative of the bottom, and then we're going to retry the limit. So this would be g prime at negative 2 plus 2 times negative 2. And then the bottom part would be 2 times negative 2 plus 4. Well, 2 times negative 2 plus 4 is 0, right? And g prime at negative 2, let's see, g prime at negative 2. So now we're looking at g prime at negative 2 is 4. So this equals 4 plus 2 times negative 2, that's negative 4. Uh-oh. I did L'Hopital's rule. We did it correctly. We found the derivative of the top or the derivative of the bottom, took the limit again, and I still get an indeterminate form. What do I do? If I still have an indeterminate form, that means I can do L'Hopital's rule again. And so in the second iteration, I guess, or the third iteration, we're taking the limit as x approaches negative 2. We're going to take the derivative of the top over the derivative of the bottom, and we're going to try it again. G double prime at negative 2 plus 2. Let's see, what is g double prime at negative 2? We took the derivative of the derivative, so g double prime at negative 2 is 3. Plus 2, that's 5, right? There's a plus 2, that was the derivative of 2x. Oh, and then the denominator is just divided by 2. So here's our answer. There is an answer. There is a limit. However, in this case, we had to do L'Hopital's rule twice, right? And the reason we could do L'Hopital's rule twice is because after we did it once, we still got an indeterminate form, 0 over 0. And so that tells me that I'm eligible, I'm able to take the derivative of the top or the derivative of the bottom and do L'Hopital's rule to figure out the answer. That, in a nutshell, is how this shortcut works. It's a neat little shortcut, and I encourage you to put it in your toolbox. Remember, you can't use it all the time. It doesn't work for all limits. It only works for limits that are indeterminate. And when you take the derivative, take the derivative of the top or the derivative of the bottom, not the product rule. And you'll find the answer, hopefully, a little bit faster to move on to whatever else you need to do.